for the invitation. Always great to be here. So I mentioned that actually the second line is actually a subtitle. It's not part of the title. Kidding. So yeah, I want to talk about like the joint calibration of the S&P and the VIX. It's a long-standing issue in quant finance, and as you can see in the title, I claim that the puzzle is solved. So you'll see for the first time, I think, I'm sure, today, like a model that calibrates exactly to market data on the S&P and the VIX. And the way I solved the problem was using optimal transport, and so in particular Martingale transport, and even like a new kind of Martingale transport that I have called dispersion-constrained Martingale transport. So in particular, it will use some of the concepts and techniques that Beatrice has introduced in her talk earlier this morning. So thank you again, Beatrice, for making my job easier in this talk. Okay. So you know that volatility indices, such as the VIX, of course, there are indicators of volatility in the market, okay, like you take the temperature, but it's much more than that. You have futures and options that trade on those volatility indices, and they're widely used to hedge the volatility exposure of options portfolio. And the fact that there exists this liquid market for futures and options on volatility indices has led for the need for models that jointly calibrate to the options on the underlying and the options on the derivative, on the volatility indices. Okay. In particular, you could today have two desks within the same financial institution, one SPX desk and one VIX desk, and they could actually easily arbitrage each other because they're somehow ignoring the very strong links between the S&P and the VIX, because the VIX is just the 30-day implied volatility of the S&P. But if you ignore that, it's easily to arbitrage each other. So in particular, since VIX options started trading in 2006, many practitioners and researchers have looked for models that jointly calibrate to market data, both on the S&P and the VIX, so VIX options and VIX futures. But no one was able to build a model that exactly calibrates to the data. It's known to be a very challenging problem, and especially for short maturities. So today I'll explain how you can actually build such a model. So why is it a difficult problem? When you look at the data, short-term data, you observe like a very large negative skew on the S&P. Okay? So the implied volatility as a function of the strike has a very strong slope, negative and very large in absolute value. So that means that in classical stochastic volatility models, you will need large volatility of volatility to be consistent with that. But if you have large volatility of volatility, that means that the VIX options have a large implied volatility, because vol of vol is directly what drives implied volatility of VIX options. That's exactly what it is. And actually, for instance, if you take the double mean reverting model that was suggested by Gadrol, Jim Gadrol was one of the first to investigate this joint calibration issue, actually you see that if you want to be well calibrated to the VIX options, then you will not have enough skew in the S&P. Okay? And if you're well calibrated to the skew on the S&P, the vol of VIX options is too large in your model. So you will want to decrease the vol of vol, but then you will decrease the skew of the S&P that's already too small. Okay? So you see like this competition between, if you want one handle, which is the vol of vol, that controls two different things, and it's hard to be consistent with both. Okay. So I have myself done like quite a lot of numerical experiments. I'm here presenting just one example using a rough volatility model, but it's just for the sake of introducing those this skewed rough Bergomi model. So basically, it's just like the classical rough Bergomi model, but now with mixing two processes. Okay, so the instantaneous variance is now a mixture of two exponentials, okay, of rough volatility processes with two different volatilities, nu0 and nu1. The fact that you mix those two exponentials allows you to recover the positive skew in the VIX smile. This, by the way, was independently suggested by Stefano here in the room. So this is market data, VIX options for shortest maturity here, 1 month, 2 months, 3 months, 4 months. So you see that the positive skew, so the larger the vol, the larger the vol of vol. That's typical of volatility options. That's just market data. And you see that for the different maturity here, I show you that with this skewed rough Bergomi model, you can well calibrate here for the maturity 1 month, 2 months, 3 months, 4 months. Okay, very decent calibration, not perfect, very decent. But then if you look at the options on the S&P, even if you put the minimum possible or maximum negative correlation between volatility and spot, which is the one that will give you the maximum negative, maximum negative slope on the S&P SMILE, you see that market is in red. You see that you don't have enough slope. So in absolute value, the slope here, the blue slope, the model one, is not large enough. Okay, and this is for 2-month maturity and then 3 months. That's typically what you get. So that was the first approach where, So I should mention that I get exactly similar result for plenty of models, including like the non-rough, so just the classical 2-factor Bergomi model, but skewed so that you can reproduce this positive SMILE. Okay, so that was an approach where I first tried to calibrate to VIX options, and then I just used the extra parameters, which is just spot-vol correlation, to try to calibrate to the S&P options. But I could do the opposite. I could first calibrate to the S&P options, and then try to calibrate to VIX options. So a classical way of doing that, you would consider all the continuous models on the S&P that are calibrated to the S&P SMILE. They are of this form, right? We know that you can, A is just any stochastic volatility model, okay? And if you just decorate it with a leverage function, which is the Dupire local volatility here divided by the square root of the conditional expectation of the instantaneous variance given the spot, this describes all the calibrated models, continuous models calibrated to the S&P SMILE for a full surface of implied volatilities. And then you can, so any choice of A will lead to a model that's calibrated to the S&P SMILE, and then you can optimize on A so as to calibrate to the VIX options and VIX future. Okay. And if you do, so of course it's hard to optimize over all A because it's all stochastic processes. Okay. They can be anything, by the way, and they can have jumps, they can be rough, they can be whatever. What I did, of course, is just experimenting with some reasonable ones. So, for instance, a 2-factor Bergomi model for 80, and skewed so that you can reproduce the positive VIX SMILE. So it's a lot of parameters. And when you optimize on all those parameters on 80, each time you're exactly calibrated to the S&P, but you see like actually the best SMILE that I get for VIX options is way larger than the market SMILE. Okay? So it's consistent with what I said before. If you're calibrated to the S&P SMILE with a very large slope, then actually you will get an implied vol of the VIX that's way too high. There are some other papers that found basically the same. So Yuri, for instance, here in the room, has a nice paper with Jean-Pierre Fouque where they consider Heston model with stochastic vol of vol to try to do the joint calibration stuff. But actually, their method is actually valid only for the maturities that are below 4 months. But precisely, it's actually below 4 months that it's difficult to do the joint calibration stuff. So we can't really use their result here. Let me skip maybe this one. And so recent paper by Jacquier, Martini, and Muguruza, where they also mentioned that in, for instance, the rough Bergomi model, you have a 20% difference between the vol of vol parameter obtained through VIX calibration and the one obtained through SPX. Okay? This suggests that the vol of vol in the SPX market is 20% higher when compared to VIX, revealing potential data inconsistency, arbitrage question mark. So clearly, this is not correct because the fact that this class of models cannot explain market data, is not consistent with market data, does not mean that there is an arbitrage. It just means that the model is inconsistent with market data, period. Okay, so, and we will see here that there is no arbitrage. So many other people have tried to do this joint calibration, solve this joint calibration problem incorporating jumps in the dynamics of the S&P. I'm citing some of the authors here. Because indeed, jumps, they will offer extra degrees of freedom and allow to partially decouple the S&P skew and the implied volatility of the VIX. But all the attempts so far only led to approximate fits. Okay? They are not too bad, but they are not exact fits. So you cannot, it's not a model that is exactly calibrated to the market data. So the way I approach this problem to build a model that's exactly calibrated is actually completely different approach. So instead of postulating a maybe jump diffusion model parametric, I will use a non-parametric discrete time model. Okay, so completely different. And that will allow me to decouple the S&P skew and the VIX implied vol, and also to perfectly fit the SMILEs because it's non-parametric. So precisely, I will consider a VIX maturity T1. T2 will be T1 plus 30 days. And I will build a joint probability measure on 3 things, which is the S&P at time T1, S1, the S&P at time T2, S2, and then V, that's the VIX at T1. Okay? And that joint probability measure will be perfectly calibrated to the smile of the S&P at T1 and the smile of the S&P at T2, and also to the VIX future and the VIX smile at T1. And on top of that, of course, that's super important, the model will satisfy the Martingale constraint on the S&P, and also the consistency requirement, if you want, that the VIX at T1 is indeed the 30-day implied volatility of the lock contract. So that's just a consistency condition. And so this discrete time model is actually cast as the solution of what I call a dispersion-constrained Martingale transport problem, and it's going to be solved using the Sinkhorn algorithm in the spirit of a recent paper by Pierre-Henri Labordère and Adrien Demarche. So very quickly about notation. For simplicity, I assume zero interest rate repo dividends, but of course I have them in my numerical experiments. Mu1 will denote the risk-neutral distribution of the S&P at T1, mu2 for T2, mu-v will be the one for the VIX, because you get all the VIX options. So of course, if you interpolated, extrapolated your market data. FV will be the VIX future at time 0 for the maturity T1. Okay, I will simply assume that the log has a finite price, okay, the log contract, and also the VIX squared. Okay, that's the only very mild assumption that I'm making. You know that no calendar arbitrage in the S&P without like using the VIX just means that mu1 is smaller in convex order than mu2, and so that's what we're assuming here. So as a reminder, the VIX, by definition, is such that the VIX squared is the implied volatility of the 30-day lock contract. So tau denotes 30-day, and that's exactly the definition of the VIX at time T1. So I will use the notation L for minus 2 over 2 log. So it's basically the negative of the log. That's this convex function here. OK, so on the way to building the model, I need to be clear about what is an arbitrage. And for this, I will first need to be clear about superreplication and duality. So I have this. I'm taking this as an example. Imagine that you are interested in a forward start option that will pay a certain payoff f of S2 divided by S1. Okay? So S at T2, S at T1. So you know that if you just know the marginal distributions at T1 and at T2 given by the vanilla options, that gives very little information on the joint distribution S1, S2. Okay? So you have a lot of possible prices for those options. And precisely, so computing the upper and lower bound is exactly the subject of a classical optimal transport. Of course, in finance, when you know that S is actually an asset, that you can actually you can delta hedge at time T1 for zero cost, and that's telling you that S1, S2 has to be Martingale under any risk-neutral measure, and so that has led to the development of Martingale optimal transport, initiated and introduced by Pierre-Henri Labordère in 2012, and he has a nice book about it. But on top of that, when you know that S is the S&P, you have extra information, because you have all the VIX future and VIX options information that constrain even more your problem. And that will lead to what I call dispersion-constrained Martingale optimal transport. So we'll see that. So how is it? So following the seminal paper by Stefano De Marco and Pierre-Henri Labordère, and that we continued with Marcel Nutz and Romain Menego, we are considering the following hedging instruments. So imagine you want to super replicate some payoff F of S1, S2, and V, can be in general. So what you can do, your available hedging instruments will be the vanilla options on the S&P, maturity T1 and T2, and also the options on the VIX, okay, because you have this available. So the cost is simply the market price of those positions. And also, at time T1, you can delta hedge yourself. So delta hedge in the spot, or delta hedge in the lock contract. The price at time T1 of one lock contract that will deliver L of S2 over S1 is precisely V squared by definition of the VIX. Okay? So, and the cost of this is zero, because it's just delta hedge. You see that the deltas here that I will decide at time T1, they can depend on S1 and V, because those are known at time T1. Okay? So those are my hedging instruments. Just remember these shorthand notations for this delta PNLs. I will denote them by delta S and delta L, okay, just to save space on the slide. So you have a payoff F, for instance, F of S2 over S1, if it's a forward start option. You want to super replicate it using those hedging instruments that I mentioned before. Okay, so you're considering all the super replicating portfolios. U1, UV, U2 are the vanilla options, delta S, delta L, the two delta strategies that super replicate F in all possible states of the world. And then you're interested in the cheapest super replicating portfolio. And that's exactly an LP problem, right? You have your parameters U1, UV, U2, delta S, delta L. They satisfy linear constraints, and the objective is linear. So that's, of course, each time you have linear program, you have a dual. And the dual problem is simply one of maximizing the risk neutral expectation of the payoff, F of S1V and S2. And what are all those risk neutral measures? They are the measures, so that's denoted by this set P, calligraphic P. That's super important in the rest of the talk. So it's important that you remember what this is. It's all the probability measures on so S1, V, and S2 that have the correct marginals that are given by the market. And on top of that, that satisfy the martingality constraint and the consistency condition that the VIX is indeed the 30-day implied volatility of the lock contract. Okay, so this is the martingality constraint on the spot, and that's the consistency condition. And so this is really a dispersion-constrained martingale optimal transport, because here, of course, this condition here is telling you that when you know, when you are T1, so you know S1 and V, that gives you the average of S2. And this second condition is giving you a condition on the dispersion around the average, which is S1. Okay? So that's given exactly by the VIX market. So it's easy to prove just by following the proof in the seminal paper by Henri Laberder, Begelbock, and Penkner, that the two problems, so the primal problem. So yeah, here I will say primal for the physical problem, which is the financial problem, because that's really the primal thing. And I will call the dual the abstract one, which is the one with the probability measures. Okay. And the primal and the dual, they lead to the same price, okay, same value. So in particular, so going back to the forward start option, I'm just adding the last two points here on the slide. So when you add this VIX market data, it may actually possibly reveal a joint S&P and VIX arbitrage. And that corresponds to the fact that this set calligraphic P would be empty. We'll see this in a minute. And in particular, if you look at the limiting case where this set P would be just one singleton, that would mean that if you add the VIX information, you would have exactly one price for the forward start options. Okay. Of course, there's no reason why it should be just a singleton, but it's interesting to know. Okay, so what do I call an arbitrage, a joint S&P and VIX arbitrage? Remember, like the portfolios that super replicate F in general, that was denied by UF. So here it's just U0, so just a portfolio that super replicates 0. And I say that I have an arbitrage if I have a portfolio like this, super replicates 0, but that has strictly negative price. Okay? And of course, equivalently, because you can scale the portfolio, that corresponds to the infimum over all the U0 being minus infinity. There is a clear arbitrage, joint arbitrage between the S&P and the VIX, if this equality here is not satisfied. Okay? And that's trivial to see here. You just take this static position in vanilla options, maturity T1, maturity T2, with just the lock contract, and you delta hedge with just one lock contract at time T1, with just UV being the V squared, and you see that you need to have this equality. So you can make money without any risk if this equality is not satisfied. And actually, there has been reports that this equality has already been violated in the market, but actually, I don't know how to make sense of those reports, because actually the two quantities that are here on the left-hand side and on the right-hand side, they do depend on extrapolations of the smile. The VIX smile on the left and the S&P smile on the right. And actually, you can make both sides of the equation as large as you want. Okay? They can go all the way to plus infinity, depending on the extrapolation that you use. So actually, yeah, all the violations that have been reported, they are based on some arbitrary, but some arbitrary extrapolation of the smiles. Okay. Yeah.
Sorry, you can still approximate what is on the left, approximate what is on the right, with the finite slice you have.
Yeah.
And hope for the best and hope that the arbitrage is still there at maturity, right? I mean, you can still try to play your arbitrage out of the violation of this.
But what do you mean by a violation of this? I mean,
if the difference between left-hand side and right-hand side is large enough,
yeah?
yeah. One point wall, then
Yeah.
you can discretely approximate the left-hand side, right-hand side, and try to play this portfolio statically, and this will give you an arbitrage.
Well, then I can tell you that I can change the extrapolation of one of both sides to make them equal. So, and then if you want, the arbitrage disappears just because you changed some implied volatilities for very large or very low strikes. So it's not indicative of any arbitrage to me.
This I agree.
Yeah.
Okay, well,
So what I do in the numerical experiments is I will always consistently extrapolate the VIX and S&P smiles so that this equality holds in all my numerical experiments. So it's easy to prove that the market is free of this joint arbitrage if and only if the set calligraphic P is non-empty. And that's also equivalent to saying that there exists a coupling between S1 and V, so the two quantities at time T1, such that two distributions are in convex order, but there are two distributions in dimension 2. So the first one is S1 L of S1 plus V squared. So for this, you see you need a coupling of S1 and V. And the second one is just the distribution of S2 L of S2, which is supported by a graph, right? And so if there exists, so all this is equivalent, okay? So existence of a coupling such that the two distributions are in convex order, which of course means that you take any convex function f in dimension 2, and you need to have this inequality. So the fact that 1 is equivalent to 2 is just using the absence of a duality gap that I mentioned before. And the fact that 2 is equivalent to 3 is actually very easy when you see that the two conditions, remember the Martingale condition and the consistency condition, so the two conditions that are described by those conditional expectations, they can actually be written simply as just the expectation of M2 given M1 is M1, so it's a Martingale condition. If you define M1 and M2 like this, and then when you use Stratton's theorem, you see that that's equivalent to the fact that there exists a coupling in U such that the two measures here are in convex order. Okay, so that's exactly what I mentioned in the theorem. So if you want to prove that there is no arbitrage, joint arbitrage on between the S&P and the VIX in the market, which was unknown, until today, we don't know how to do that. So either you solve this LP problem, okay, as I mentioned, but that's not easy because you have plenty. So first, the parameters, they are in infinite dimensions. Okay, it's all functions. Even here, that's function of two variables, and you need to try them all. And on top of that, you need to check the superapplication constraint everywhere. That, of course, numerically, you will need to discretize. It looks more handy to try to check number 3 directly, but the problem is that in dimension 2, the extreme rays of the convex cone of convex functions are dense in the cone. Okay, so basically that means that, and that's of course in contrast with what happened in dimension 1. So from the Blaschke-Pick result in 1916, we know that the extremal convex payoffs are just the call and put payoffs, right? So in dimension 1, if you want to check that two things are in convex order, that's easy. You check that they have the same forward value expectation, and you just compare all the prices of, let's say, call options, for instance. But in dimension 2, there is no simple characterization because basically you would need to try all the convex functions in practice because they are dense in the cone. So instead, we will actually directly verify the absence of joint arbitrage directly by proving that P is non-empty. But of course, if I prove that P is non-empty by building an element in P, I'm actually solving the initial problem, which is building a model that's exactly calibrated to the S&P and the VIX option data. So that's what we'll do in the last part of my talk and showing you numerical results. Okay, so how to build this model mu in the set P? Okay. So again, it's very inspired by the recent paper by Henri Labordère and Demarche. So we're assuming that this set P is non-empty. We try to build an element mu in this set, and actually we are fixing a reference measure, mu bar, on S1, V, and S2. It can be whatever you want. It's something that could correspond to a view or just something simple to use in the numerical experiment. And then we will look for the measure mu in P that is closest to mu bar for some distance, and we take the relative entropy with respect to mu bar. Okay, and that's again here defined here. And the beauty of this one, as Beatrice mentioned in her talk, is that now we are, instead of like a linear problem that we had before, we have a strictly convex problem. that we can easily solve after dualization using Sinkhorn's fixed point iteration algorithm. So actually here an extension of Sinkhorn. So you see that here, compared to a Beatrice stoch, I'm not, you see there was a cost function plus epsilon times the relative entropy. And actually here, the cost is 0, you see? It's corresponding to a payoff that's 0, because I just want to check that P is non-empty. So I want to super replicate 0, and if the super replication price of 0, or let's say I want to sub-replicate 0, so if the sub-replication price is 0, so that means that, yeah, the set P is non-empty. And if the set P is empty, then I will get minus infinity, right? And so it's the same thing, even if it does not look exactly like the same, but the cost is 0, and the epsilon you don't care because I don't have any cost here. But it's the same. And again, so how do I build this mu? Okay, so here it's not easy because you have all the constraints, right, in P. So I will use Lagrange multipliers, okay, to actually write the thing in a dual form. So that's exactly as Beatrice mentioned. And so, for instance, here, if I want to make sure, so mu is just all the probability measures. Okay, U are all the portfolios, vanilla options, and the deltas. Okay, so here, the constraint that the first marginal of mu must be mu1 is, for instance, here completely in the fact that when I take the sup over u1, this, okay, will be plus infinity, except if the first marginal of mu is mu1. Okay, so that's a way to integrate the constraints in this using the Lagrange multiplier. U1 plays the role of the Lagrange multiplier. And actually, those two deltas here, you see there's nothing offsetting them. It's because the price is 0. That's correspondingly exactly to the set S of Beatrice. Like all those possible payoffs must have 0 expectation so that it's a Martingale and it satisfies the consistency condition. And if you assume that you can apply the minimax theorem or like no absence of a duality gap, then you can swap the sup and the inf. And the beauty is that now the inner infimum can be exactly computed. So this is the inner infimum over mu. Okay, so this is just a constant term, does not depend on the mu. So it's of the form the relative entropy, mu bar, minus the expectation of the mu of some random variable x, which is this red one here. And we can actually exactly compute it. And we know exactly also where the infimum is reached. Okay, and it's reached at mu bar x, which is just defined through the Radon-Nikodym derivative with respect to mu bar. And it's simply the Radon-Nikodym derivative is simply the exponential of x renormalized, where x, again, is this red stuff here. So we know everything. So the initial d mu, remember, so that's minimizing the distance between mu and mu bar, corresponds to exactly maximizing a function psi mu bar of u. That corresponds to my primal problem after dualization. And this psi mu is just the constant term minus the log, the expectation of the mu bar of exponential x. Okay, that is here. So actually, we know that this minimum distance is not plus infinity if and only if P is non-empty. And in that case, the minimum is attained just by classical topology argument. If the supremum defining P mu bar here is also attained at, say, some U star, then we know that the infimum defining D mu bar is actually just this mu star that, remember, mu bar times the Radon-Nikodym derivative, which is just the exponential of x renormalized. Okay? So if we solve the problem for P mu with this U, we got exactly the mu star that we want. Yeah, let me skip those details. So what's important is that just by duality, we had an initial difficult problem which was minimizing over mu in P, but P has a lot of constraints, while now we are just optimizing a strictly concave function, but without constraints, because the U are just all possible portfolios. And so, of course, you optimize a concave function, so you just cancel the gradient, okay? And then it's all about like solving numerically this equation. Of course, you don't have to look at the equation, but basically what's important is that you get U1 if you know all the others, UV, U2, delta S, delta L. You know UV if you know the others, U1, U2, delta S, delta L, okay, and so on and so forth. So that, yeah, paves the way for an iteration algorithm, which is exactly the Sinkhorn algorithm. So in the interest of time, I should skip the detail, but basically, if at time n you have, at iteration n, you have an estimation for your portfolio, okay, so you get un plus 1 that you plug in here, that gives you UV n plus 1 that you plug in here with the U1B that gives you U2 n plus 2 and so on and so forth. And interestingly, each one of those lines here corresponds to a Bregman projection, which means that at this step here, you're exactly calibrated to the smile of S1, but not to the other smiles. Then at the next step, you're exactly calibrated to the smile of V, but not exactly to the smile of S1 and S2, okay, and so on. But of course, when you iterate, and converge, then you converge to a model that's exactly calibrated. So I will skip the implementation details. I'm happy to talk after for those who are interested, but just in the interest of time, in the last minute, I want to show you numerical results, of course. So this is, for example, the S&P at time T1, which is 21 days, the first maturity, the VIX at time T1, and the S&P at time T2, so that was as of August 1st, 2018. So you see that the model calibrates like super nicely to the three smiles. On top of that, S is really a martingale, in the sense that here it's the price of S2 minus S1 divided by S1, given S1 and V for a grid of S1 and V, and it's strictly 0. You have to look at here, it's 1 to the minus 15, right? So it's really strictly numerical 0. And the same for the consistency condition. V is really the price of the VIX, because the price of log of S2 over S1 minus V squared divided by V squared is strictly 0. What is the model? What does the model look like? So if you just look at the probability distribution given S1 and V, it's something that looks actually quite familiar and classical. You can, of course, define a local VIX squared, which would be the conditional expectation in the model that I built of V squared given S1, and we get the traditional decreasing structure. And if you look at the conditional distribution of S2 given S1 and V for different values of S1 and V, so you see like 3 values of S1, small, middle, large, and different values of the V corresponding to the different variants, we get actually something that's quite classical, where we have a large left tail for S1 in the middle, but a large right tail for the S1 quite big. In the end, when you average everything and you look at just at the distribution of log of S2 over S1 divided by V square root T plus 1/2 V square root T, so that's the classical, just a standard Gaussian, in the Black-Scholes model, for instance. Here you see, but you're averaging over all the possible values of S1 and V. Here, you see that you eventually have a left tail that's fat, okay, so a fat tail to the left, and that's so that's the price of forward starting options as a function of the strike in that particular model, and that's the corresponding U1, UV, U2. So U1 and U2 corresponds to like smooth cold payoffs. Just 1 minute. So that's the delta S and the delta L, so the two deltas on the spot and on the log contract. Interestingly, they have the same shape. I don't really know why, but they have the same shape, both of them. That's just like for the second maturity, really same story, so I skip it. It works exactly the same, and it's also the same shape for the two deltas. And I just want to show you just December 24, because that was like a turmoil on the S&P market, so just to show you that even when the volatility is large, so the VIX went up 36% that day, the first VIX future, 23 days, was 26%, and you can still very well calibrate to the three smiles and to the VIX future, and you're exactly a martingale, and you have the same kind of properties for the local VIX squared and the conditional distribution. Okay, so that's the price, and you have also the same. And even in that case of very large volatility, you have also the same shape, both for the two, and same shape as for low volatility environment. I don't have to tell you about the maturity issue. You have maybe 2 days of overlap between the two VIX implements. So if you want to be extremely precise, you need to add another maturity T1 prime, but that's doable. And if you want to, of course, extend to the multi-maturity case, so if you ignore this overlap issue, it's actually very easy. You just glue models between Ti and Ti plus 1, Ti plus 1 and Ti plus 2, and it works perfect. Okay, so thank you very much for your attention, and I'm happy to take any questions.